Hi everyone, this is Mrs. Jackson, and this is going to be the last section in Chapter 2, Quadratics. And I'm calling this section 2.M for 2-point modeling. And in this last section, we're going to be looking at the applications in real world that we would model using quadratic functions. And then we're going to finish it up by performing something called quadratic regression, which is where we take a data set and we would fit a model to that data. Okay, so let's first look at, in part 1, the applications that we have in real life that we often use quadratics to model. And the first thing is anything that's under gravitational pull. So any ball thrown, any football, soccer, basketball, hockey, any kind of projected missile here, a rocket, or some kind of missile. Anything that would be thrown or projected is under the force of gravity, and that is going to always be modeled with quadratics. In terms of physical structures, a suspension bridge is often modeled with a quadratic because you get this U shape here. And then finally, we're going to look at financial analysis in terms of maximizing revenue or maximizing profit. That's almost always modeled with a quadratic function. All right, so this first part 1, we're going to be focused on a free-falling object under the gravitational acceleration. So as I already mentioned, any object that's thrown up or kicked or projected in some way is going to see gravitational force and being pulled back down to the earth. And we call this a free-falling object, and the gravitational acceleration on Earth is a constant, and anything in the air is going to see that constant or that pull back down to the Earth. The main thing here about our modeling is going to be specifically called free-falling. And by that I mean that whatever the object is, a rocket, a ball, etc., that it's seeing the uninhibited gravitational acceleration downward. And by that I mean it is not being subject to any kind of massive wind drag like a parachute, or the rocket is having some kind of fuel injection on it, which is going to inhibit that gravity fall. Okay, so that's what we mean by free falling. All right, so what is that gravitational acceleration? In the metric system, it is 9.8 meters per second squared. And this may be familiar to you for some of you who are in physics. And in the English system, it is roughly 32 feet per second squared. So what type of acceleration force we're going to use in our model is really going to depend on whether we're using metric or English units. So in the world of physics, when we're modeling free-falling objects, we're generally modeling the object's height with respect to time. And so generally speaking, you're going to see h sub t here. So the height as a function of time is going to be our function. And that physics model is going to be negative 1/2 times the gravitational acceleration times time squared plus v sub 0 times time plus h sub 0. Okay, let me take each of these terms one by one and explain what's happening here. So first, starting with the gravitational acceleration on Earth, these are our numbers here, and so these are our values that we're going to be substituting in for g in the model below. So if you look at the front here, because of this negative 1/2, now why is this negative? That's indicating downward. So gravity is always going to pull an object towards the ground, and so it is always going to be a downward facing parabola that we're looking at. So that's the negative. This 1/2 is a little bit difficult to explain without going on a huge tangent, but kind of think of it as sort of an average of an object going up and then down. And so this leading coefficient here up front, let me write that down. The leading coefficient, depending on what units you're in, is either going to be negative 4.9, because that would be half of 9.8. So the front will either be negative 4.9 or it's going to be negative 16, half of the 32. And this V sub 0 stands for the initial velocity of the object, whatever the object is. And think of velocity as speed. So it's the initial speed, if you will. So I'm going to try and force myself to call this V sub 0. I'll write this down, V sub 0. However, invariably, I think in class you're going to hear me say V sub naught, or even V naught. And this is a physics phrase. So if you're in physics now, maybe you've already heard of this, but this is something. It's a physics phrase that we use for the initial point, if you will. And then finally, H sub 0 stands for the initial height. So as you know, almost always in any real application, like think about throwing a football, that ball is not being thrown from the ground level. It's being thrown from some kind of initial height, and we need to take that into account. So again, this would be called H sub 0 or H naught. I'm going to try to stick to H sub 0. All right, so the last point I would make here is that if you're not throwing an object up or propelling something up, and you're just simply dropping it down to the ground, then there is no initial velocity. So you will see here, this would just be 0 times time, so the entire middle term just goes away if it's just a free-falling drop to the ground. Okay, so let's take a look at a real example here and see how we use this physics model to identify the height of an object versus time. And the example that we're going to look at here is a rocket launch. So if we look at what's happening here, we have a model rocket. It's launched straight upward from some kind of platform that is 6 feet above the ground at an initial velocity of 200 feet per second. So that's its initial speed. One thing I want to point out here is that the example talks about fuel propellant, and that's what's pushing the rocket off the platform. And I want you to think of this rocket is initially being lifted off the platform by this fuel. However, as soon as it's lifted off, in other words, right after launch, that is under the force of gravity. It's no longer being projected by any kind of engine or fuel of any kind at that point. If it were, we could not use this physics model, this free-falling physics model for this problem. All right, so I always recommend maybe doing a little sketch. So we have some kind of platform here, and that platform is 6 feet above ground. And we have our rocket here. And that rocket is going to be projected straight up, and it's going to hit some peak, and it's going to fall down to the ground. Okay, so the vertex here, I'll put H comma K for our vertex. That's going to be the rocket's highest point before it starts going back to the ground. All right, so we're going to start out with our free-falling model. The height of an object is negative 1/2 g times the square of time plus v sub 0 times time plus the initial height. Since I'm seeing that our initial velocity is 200 feet per second, I know I'm going to be using my English units for the gravitational acceleration. So my model then would be h of t equals -1/2, and our English gravitational acceleration is 32 feet per second squared times time squared. Our initial velocity is 200 feet per second, so I'm going to substitute 200 in there, and our initial height is 6 feet. So if I just kind of tidy up the model here, I've got a leading coefficient of -16 t squared plus 200 t plus 6. And this is going to be our model that models our height versus time of this rocket. Okay, so the first question for us is, when will the rocket reach a height of 336 feet? And so when we're being asked when, you can see we're basically being told to solve for t. When means time. And 336 feet, that's our output, that's our height, which is the output. Okay, so I'm going to use our initial model that we created, and I'm going to flip it around. It's just going to be a little bit easier here. So I'm going to say -16 t squared plus 200 t plus 6 equals h sub t. I'm just flipping that around a little bit. It's just a little bit easier to solve. Now our h sub t right now we're being told is 336 feet, so I'm going to substitute that in. And then I'm going to solve for t. So our output is 336 feet. And if we're going to solve for t, we could do that by factoring. We could do it by completing the square. We can use the quadratic formula. In any case, we're going to get that 336 over here to the left. I'm going to subtract that from both sides. And when I subtract it from the left, I'm going to put it under its like term, which is the constant. And finally, we have -16 t squared plus 200t minus 330 equals 0. So in this case, in all cases really in real world applications, you're going to see some big numbers, okay? So it's not going to be as comfortable to factor, it might not be factorable, and you might spend a lot of time trying to see if it's factorable. So when it comes to real world applications, I think I would recommend almost always using the quadratic formula. And then you can plug everything into the calculator at once and get a solution fairly efficiently. Okay, so if we look at our equation here that we have, you can see that every number here in terms of the coefficients and the constant are even numbers. So in order to make your quadratic formula a little bit simpler, you might want to factor out as much as you can. And it's always a good idea to make the leading coefficient positive if you can. It just makes things a little bit easier. So I'm going to factor out, instead of a 2, I'm going to factor out a -2. So I'm going to put out here -2. If I factor a -2 out of that first term, I'm going to end up with +8 t squared. If I factor out a -2 from a +200, I'll end up with a -100t. And if I factor out a -2 from a -330, I'm going to end up with a +165 here, equals 0 on the other side. Now, because we're trying to solve for t, and I've got -2 as a factor over here, I can divide everything through by the -2. So essentially that -2 kind of just goes away. when we're trying to solve for t. So this is what I have. So in this case, a equals 8, b equals negative 100, and c equals positive 165. So the quadratic formula, as you recall, I'll put that color here, is instead of x equals, in this case we've got t, so I've got t equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so I'm going to start to substitute here. So I have t equals opposite of negative 100 plus or minus the square root of negative 100 squared minus 4 times a, which is 8, times c, which is 165, all divided by 2 times a, which is 16. 2 times 8 is 16. So I would recommend you get proficient at being able to put this all in the calculator at once. Doing so requires correct order of operations, however, so I would caution you that you make sure that when you plug this whole thing into the calculator, that it's surrounded by parentheses before you do the division of 16, because you need this entire quantity to see that division of 16. In any case, if you plug this, and I do want you to practice, when you plug this into the calculator and you do this positive 100 plus this quantity here, you're going to end up getting t equals 10.54. And of course, we're solving for time, so that's seconds. But when you actually do the subtraction operation here, 100 minus this quantity divided by 16, then you're going to get another value for t, which if you plug that into your calculator, you will get t equals 1.96 seconds. Now, why do we have two answers? Well, at this height here of 336 feet, I don't know where that is, but I know it's below the vertex since I got two answers here. So I've got some height here of 336 feet, and I'm going to hit that height in two different time points. One, very quickly, less than 2 seconds. I'm going to hit it. And then it's going to hit its peak and come back down. And at 10.54 seconds, I'm going to hit that height again. Okay, so what is that maximum height here? Well, the maximum height, as you recall, is our vertex. So our vertex, I'm going to put this over here. Our vertex is h, comma, k. And in this case, that independent variable h is time, seconds, and k is our height. So our formula for h, if you recall, is h equals negative b over 2a. And a point of confusion for some students is that students will go ahead and use this factored form here and use these values for b and a. And you cannot do that. We have to go to our original model that we're using to model this rocket. So make sure you go back to the original. And in this case, our b here is, in our original model, is 200, and our a is negative 16. So I'm going to use those values. I've got h equals negative 200 divided by 2 times a negative 16, and that calculates out to 6 and 2500 seconds. So remember, we're solving for time there on the h. Now, how do I get the height? I'm going to simply substitute a value t of 6.25 into my original model and calculate the height. So I'll zoom in here. Our original model is h sub t, or h of t, equals negative 16 t squared plus 200t plus 6. I'm going to go ahead and evaluate this function at t equal to 6 and 2500. So I'm going to replace my t. Everywhere I have a t, I'm going to put in 6 1/4 seconds, and I'm going to solve for that height. And you could put this in your calculator all at once. And our height at its peak, maximum height, let me call it max height, is going to equal, if you substitute this in, a maximum height of 631 feet, which is significantly higher than our point here where we were looking at 336 feet. So obviously my sketch is not drawn to scale. This peak is way, way higher than that 336 feet. But you could sort of think about this vertex then. Let me write this down here. Our vertex is at a time point of 6 1/4 seconds, and it reaches its maximum height at 631 feet. So this is our vertex. Okay, so last question. When will the rocket hit the ground? So it goes up, it comes all the way down. What is that time point? When, as soon as you see that when, we're solving for t, time. All right, when the object hits the ground, that's at a height of 0 feet. So we're going to go back to our model. And our model, again, our original model of the height is h of t equals negative 16 t squared plus 200t plus 6. And we're going to basically substitute here a height of 0. That's ground. And so I just, as a preference, I always like my function to be over to the left. So I'm going to just kind of switch this around. So my height equals 0. As we did before, we factored out what we could just to make our numbers a little bit simpler. And I'm going to factor out a negative 2 again. So this will turn back into positive 8t squared. This will be negative 100t. And this will be negative 3 equals 0. Now, if you didn't factor out that negative 2, that's fine too. You're just going to use the quadratic formula with bigger numbers. It's a little bit more unwieldy, but you'll get the same answer. So right here, I'm going to divide both sides by negative 2, so the negative 2 kind of goes away. So I've got 8t squared minus 100t minus 3 equals 0. And I'm going to use the quadratic formula. I'm not going to rewrite that quadratic formula again. So I've got t equals the opposite of b. The opposite of negative 100 is positive 100, plus or minus the square root of negative 100 squared, minus 4 times a, which is 8, times c, which is a negative 3. And that's a point of error right there. So a lot of people will make an arithmetic error there. So be aware. All over 2 times a, which is 2 times 8, 16. So if you, and you can put this all in your calculator at once. If you do so, just recall that negative and negative means we're adding this quantity here to 10,000. But when you plug this whole thing in, you're going to get 2 values of t. The first value of t is 12.53 seconds. And the other value of t is going to be a negative 3/100ths of a second. Now, in this context, a negative here, a negative time point makes no sense. Okay, so negative time is not applicable in this context. Not valid. Okay, so our time point here, our answer is going to be 12.53 seconds. That rocket is going to be back on the ground. Okay, so this was a lot, but this is one very detailed example of how you could use quadratic functions to model a free-falling object on Earth. Thanks for listening. Please subscribe.